we are looking at adjunctions. Yeah, adjunctions were introduced in 1958, but they have been around since the birth of mathematics. Yeah, they are present everywhere. And today's relatively light lecture, yeah, is all about showing different examples of adjunctions. Okay, so let me remind you what an adjunction is. Adjunction is a pair of functors in opposite directions between two categories, and this pair is said to is said to form an adjoint pair of functors if for any choice of objects from either category, then there is a natural bijection between the appropriate home sets. Naturality as in these bijections are not arbitrary, they have to satisfy certain commutativity conditions, and that's why we are talking about them. So obviously you have to understand what naturality is, and it can be looked at in this particular fashion, but let's go past naturality and look at some interesting examples. That's our main goal. So let me label this one as the first example of an adjunction. So groups to sets, yeah, the forgetful functor is the right adjoint to the free functor, because what is a group homomorphism with a free group as the domain? It is a natural extension of a map on the generating set X. Yeah, so if you take any function from X to the underlying set of the group G, then you have a morphism from the corresponding free group to group G. Yeah, it naturally extends. So this free property itself gives you this thing. Now, I will say that you can replace GR by any algebraic category where the defining axioms are always of the form for all something, 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 for all x1, x2, xn, then inside some identity holds. Yeah, so algebraic category like abelian groups. Tell me what happens in the case of abelian groups. You still have a forgetful functor down to sets, but what is the free functor? Free abelian group on a given generator, which is simply direct sum of x many copies of Z. Okay, then R mod for any ring, same thing you do, direct sum of x many copies of this. Then perhaps, what should I say? Lattices will also work, lattices and lattice homomorphisms, that's also an equational theory, so therefore that will also work. Rings will also work, and I will leave it as an exercise, not fields, but rings will work. And let's go to a second kind of example. Okay, so these are some, this is coming from set theory, very basic set theory, and this is all thanks to Howard Curry. Yeah, name of a mathematician, not Indian curry, remember that. Okay, so we have to look at this particular pair of functors. So let us fix some set B. Then I am going to define two functors. So blank cross B, yeah, that's always a functor. Take any set A and output A cross B. What is the morphism? If there is a morphism from A to A prime, then what is the morphism from A cross B to A prime cross B? Cross identity, correct. And in the reverse direction, you take the home set from B. Okay, so let me write down what I am trying to say in the form of bijection. So sets, for any sets A and C, what I am saying is this. the set of functions from two variables, set of two variable functions a cross b to c is in bijection with this set of functions from a to the set of functions from b to c. Okay, so this is the second, the right hand side is simply a sequence of functions or a family of functions from b to c indexed by elements of a. Yeah, so this is a standard currying-uncurrying bijection in set theory, and this is actually a special instance of an adjunction. Yeah, if you want me to write down what is happening, if you are given f from a cross b to c, I can write it down for you. Then this particular function will be mapped to a function g, which is from a to the set of functions from b to c, where little a is mapping to ga from b to c, which takes a little b to f of a of f of a comma b, and then this is a bijection. You can verify that this is indeed a bijection. It will take some time, but not hard. Okay, so this is currying and uncurrying, and it's commonly used in computer science as well, yeah, because it allows you to express two variable functions as a family of one variable functions, and computers only like to talk about one variable at a time. Okay, so let's go ahead and look at some more interesting examples. For example, we can, I can also talk about top two sets. That's a fundamental example. Yeah, but the thing is always U, forgetful functor from U to sets, from top to sets. And does it have a left adjoint? Or does it have a right adjoint? I'll give you 1 minute to think about it. Given a set, can you topologize it? Discrete and indiscrete topology. So which one will work? Discrete one will work as? Discrete one will be a right adjoint or left adjoint? Okay, let's test your theory. Discrete topology, you are saying it's a right adjoint. Now you think it should be left? Exactly, any map from a discrete space is continuous, it should be left adjoint. So discrete space is like this. You should be able to verify this, but indiscrete is not going in vain either. That will be the right adjoint of this forgetful functor. So this particular functor has both left and right adjoints. Yeah, very interesting. So, I mean, what's happening here is I'm writing this chain. It's a chain of 3 functors, and yeah, everything is happening in a natural sequence. I'll give you one more similar kind of example. The question is, how many such functors can you write down in a sequence? Normally we have just 2, but now you found something which has 3, sequence of 3 functors. Yeah, 2 going this way and 1 coming back this way. Okay, now how can we extend this? Well, let's talk about this. Cat and sets. Do you remember what cat is? Small categories. Small categories. So, can I go from categories to small category to sets? Collection of objects. So, very good. So, I will call it ob. Okay. Does it have a left adjoint? Given a set, can you categorify it? There are two ways to do it. Okay, tell me, what is the first way?
One is like every home maybe is a singleton set.
Every home maybe is a singleton set, correct? And that's a pre-order. Yeah. So that one I will write as I. Yeah, so I is the maximal pre-order. On a set. Maximal pre-order on a set, like any two elements are comparable. Yeah, that's always a category. So, okay, then is there any connection between ob and I? If I'm given, yeah, so we always have to try in both senses, yeah. So from objects of a category C to a set X, yeah, this is the home in which category? Sets, correct. And on the other hand, you have the collection of functors from C to IX. From every object, you are choosing something. For every object, you are assigning some element of the set X. Will that be a functor from C to IX? You understand IX? It will be a functor. Yeah? Because you just have to, exactly, home AB is always non-empty, so therefore you can map all morphisms to that unique morphism. So there is no choice involved either. Yeah, so you can always extend this, and can you go back as well from given a functor from C to IX? Is it literally just a set function from the collection of objects to X? Functions from?
Because for functor we have object functions and
right.
Morphisms. So I will take only the object.
Morphisms are irrelevant. Yeah, you always map them anyway. So therefore, indeed, there is a bijection, and therefore, I is actually a right adjoint to the op functor. But just like the topology case, yeah, the story doesn't end here. You can always treat a set as a discrete category, small discrete category, right? You just declare the elements as objects and identity morphisms. So therefore, we also have a further morphism over here, which we are calling D. Yeah, D is the discrete category functor on that object. And yeah, it's not too hard to see that this is actually a left adjoint to the object functor. Because what's happening? Well, maybe I should write it if just to make sure you understand this. So cat dx comma c is in bijection with sets x to ob c. A function from x to the objects. Yeah, what is a functor from dx to c? Well, it's just an object-to-object assignment. You don't need to think about morphisms because identities always go to identities and identities are the only morphisms. So that's all you need to worry about. So this is indeed true. Yeah, but the story doesn't end here either. There is a further functor from cat to sets, and I will denote it by pi 0. Pi 0, like you have studied pi 1. Pi 1 is the homotopy group. Pi 0 is the path connected components functor. So path connected components of a category, you can also do that. So pi 0 is, connected components basically. And how do you obtain the connected components? If you remember, we underlying graph and then take the connected components, but there is also a categorical way of doing that. If you remember, we described congruences. So this is the maximal congruence. You quotient out by the maximal congruence. Yeah. What you do, like whenever F is a morphism, then identify domain F and codomain F. That will collapse everything to one object. So therefore it's just the set of connected components. Yeah, if there is a finite zigzag of morphisms between 2 points, then you will always get they will always lie in the same connected component. So that's a further left adjoint of D. Okay, so therefore now we have a chain of 4 functors, pi 0 to D to ob and I. Yeah, we are playing with very simple examples over here. Okay. Then we can also do some more standard examples, let's say from algebra. And in algebra you might have heard of home tensor adjunctions if you have studied enough advanced algebra. So I'm going to do it in the most general setting for now. So let mod R and mod S denote the categories of modules, categories of right R and S modules respectively. Okay, and let NRS be an RS bimodule. Okay, if the rings are commutative, you don't have to worry about these things. You just need something which is a module over both of them. Then what will happen? The common way of writing things is like this. So I'm just going to write this tensor. So a right module is always written by writing R on the right. Okay, then tensor over R. Yes, tensor over R denotes that you can pass scalars from R across the tensor symbol. And then finally NRS, which is the bimodule. But what we are using here while constructing this tensor product is that it is a left R module. So you can always take one right R module, tensor it with one left R module, and you will get an abelian group. But because N is also a right S module, so this particular tensor product will be a right S module. Okay, this is too much algebra if you haven't seen that, and let PS be any arbitrary right S module. then I'm taking their home as S modules. Because the tensor will consume R module structure, so the tensor product is just a right S module and P is a right S module. Yeah, so therefore home over S, and this is an abelian group, that's all. Yeah, the ultimate product, and there is an isomorphism of this abelian group with another abelian group, which I will write now. So MR is just the right S module, and then home NRS PS. And what should this home be about? Which scalars are we killing? No, the second home inside. Internal one is about S. Yeah, because that is the common thing. Okay, but because home is contravariant in the first component, so out of NRS, N is a left R module, so therefore when it comes out, it becomes a right R module, and therefore home MR to this right R module, I have to write home R. Home R is the simple notation for home in mod R, and home S is the notation for home in mod S. So there is this home tensor adjunction. Okay, and this is a standard fact from algebra. You cannot work with tensor products if you don't know this, but I want you to see the similarities between example 2 and example 5. Okay, so I'm going to write down what this is. So this is mod R and this is mod S. The functor is blank tensor NRS, and the other functor is home sub S NRS blank. Can you see the similarity? In 2 we had product, over here we have tensor product, and the right adjoint is still home.
Home of R and S, PS is a left R module.
No, home N comma P is a right R module because home is contravariant. So because N is a left R module and it's in the first component, it becomes a right module. You have to write those things down, otherwise yeah, it can become confusing. But I gave you the most general form anyway. Yeah, so it's very similar to what this is. And I mean, what is a morphism? Module homomorphism from a tensor product to another module. It's always a bilinear map. So it's like a 2 variable function which behaves nicely. So that way also you can compare. Yeah, A cross B to C and M tensor N to P. Any questions? Okay, then let's proceed. Now I'll give you an example which is more category theoretic in flavor, but it has some components from usual mathematics. So I'm going to define a category idem. Idem is the category of idempotents. The objects are A comma E, where A is a set and E from A to A is an idempotent. Okay. Then what are morphisms? A to E to B to D. I'm going to say that F is a morphism if, what should it commute with? The idempotents. Idempotent, you understand? What is its, yeah, that means E square is equal to E. Okay. So A comma E to B comma D, a morphism is simply a set function which satisfies certain properties. And what are those properties? df should be equal to fe. Yeah, so any set function which satisfies these two properties, this property is a morphism in this category. Now, from the category of idempotents to the category of sets, obviously we have some functor one functor. You can always give me an example of one functor. Identity functor? No? Identity is irrelevant here. Oh, identity in what sense? Okay, maybe you are onto something. From where to where?
A comma A, E goes to A.
Just a moment.
A comma E to A.
A comma E to A, forgetful functor. Yeah, but let's not worry about the forgetful functor. You are talking about?
That's what I said. A comma E to A.
Okay, no, we don't want to talk about forgetful functor, but maybe we can send it to something more meaningful which has to do with the idempotent. The set of fixed points. Okay, so the set of fixed points is a functor from idem to sets, and that's, let's call it G. Yeah, so G of A comma E we are defining to be the set of all those A's in A such that EA is equal to A. The things which are fixed. And in the reverse direction, given any set, do you know any idempotent on it? Identity. Very good. So therefore, huh? Any transposition. What is a transposition on a set?
I mean, for any x1, x2, we just flip x1, x2.
Convolution, right?
No, but transposition is not even defined on a set. So why should we talk about it? There is no minus sign, there is nothing.
Okay, but like, we can choose pairs inside this set and disjoint.
No. F of B is defined to be B comma identity on B. So that is F. Now the question is, which functor is adjoint to which functor? Which one is left adjoint, which one is right adjoint? G is left. Okay, now Suyash is saying G is right and Debajyoti is saying D is left. Which one is correct? The answer is both. Okay, so this is an example where F is a left adjoint of G and F is a right adjoint for G. Both are true. Okay, so that's why I gave you some time to think about them. Both of these identities are true. You just have to convince yourself, look at these identities for long time and then you will understand what's going on. For example, a function from b comma 1b to a comma e, a morphism from b comma 1b to a comma e, what is it? It's any function from b to a such that e composed with that function is itself. But that means it has to land inside the fixed point set. Yeah, so that's all. Yeah, so you don't have to, I mean, it's basically the image. Yeah, EA is equal to A means it's the image of the function. Right, so therefore both of them are true. So there are lots of such questions which you can ask and answer. It's very fun to play around with these ideas. Okay, now obviously if you remember, we have also done this closed set and power set or open set and power set, and that there also we looked at some examples. Now I'm going to give you something else to work with. Now this is slightly different, okay? So suppose A and B are sets and R is a relation between A and B. This is the data that is given, and define L from the power set of B to power set of A by L of B prime equal to all those A's in A such that for all B in B prime, the pair A comma B, it belongs to R. Okay? Easy to understand? And R from PA to PB is defined similarly. R of A prime is defined to be all those B's in B such that for all A in A prime, A comma B belongs to R. Okay, so these are the two kinds of two functions which are given. And obviously, because there are two functions going in opposite direction, we are talking about an adjunction over here. But there is some interesting property here, yeah, before we go about this. Are these monotone maps, by the way? Like if I increase B prime to B double prime, if B prime is a subset of B double prime, then will it be true that LB prime is a subset of LB double prime? It will be order reversing. It will be order reversing. Okay. Yeah, so both of them are order reversing because you are putting more conditions. If you increase the size of B prime, then you are putting more conditions, so the set will shrink. So actually, like, it's better to write that L is a function from PB to PA op and R is a function from PA op to PB. So now we have a pair of things going in opposite direction. Pair of monotone maps. These are both posets. Okay. Okay, both are monotone now appropriately, but note that, okay, now this is important, A prime is a subset of LB prime if and only if A prime cross B prime is a subset of R. Do you agree with this? From the definition? Yeah, because A prime is a subset of LB prime means every element there will belong. And this happens if and only if B prime is a subset of RA prime. Okay. If you understand this much, then what are we saying here? That the home set from A prime to LB prime is non-empty if and only if home set from B prime to RA prime is non-empty. Which means these home sets are in bijection with each other. But which one is left adjoint, which one is right adjoint? This is symmetric. Everything is symmetric. So therefore, yeah, so I mean, I will write it as something, but it depends on where you put the op. Yeah, it's your choice. So therefore, it's okay. We made a choice, but we don't want to commit to anything. So we say that this pair of contravariant functors are adjoint on the right. Both of them appear on the right, so we say that they are adjoint on the right. In fact, in common language, yeah, in common mathematics, L comma R is known as, anybody? As an antitone Galois connection. In practice, if you want to understand the standard Galois theory, in Galois theory, A is some set of fields and B is some set of automorphism groups. Okay, so Galois theory, entire Galois theory is all about one particular adjunction. I'm not going to go into details of what Galois theory is, because examples in this course are only for those who know that area. There is of course always monotone Galois connections which go from one poset to another. Yeah, so let me put that as the next. In practice, people don't call them monotone Galois connections. Whenever we utter the word Galois connection, then it's always antitone. But monotone Galois connections nevertheless do exist. And what will we do? We have to talk about two posets in this case, P less equal, Q less equal, and there is a pair of things going in opposite direction. Let me call this F and this is G, and if F is less equal G, then what happens? You say that F of A is less equal B if and only if A is less equal GB. Yeah, so F crosses the less equal sign and it becomes G, so it actually makes sense. It's our usual thing. Yeah, but while because we have this, we also have something more. What can you say about A and GFA? GF is monotone increasing. That's not the right language. GF is monotone increasing because G and F are both monotone maps. Yes. A less equal GF of A. Okay. Correct. And why is that true? Because you are substituting B equal to FA. And this is always true. FA is less equal FA by reflexivity. Therefore, A is less equal GFA. And similarly, what will we have? FGB is less equal B because GB is less equal GB. This is also true. Okay, now we have to give names to these things in general adjunctions. Yeah, because this is not just specific to this particular monotone Galois connection example, but this always happens. Okay, so corresponding to, I mean, this is our usual setup. Yeah, C, D, F, G. F is a left adjoint of G, corresponding to the morphism FA to FA, the identity morphism. Under that bijection, whatever is the corresponding map from A to GFA, we have A to GFA, and this particular morphism is known as eta A. Yeah, we label it eta A, and corresponding to GB to GB, 1 GB, this is happening in category C. We have a corresponding morphism in category D, which is called FGB to B, and that's epsilon sub B. Have you seen these notations before? Eta and epsilon? Equivalence of categories, yes. So equivalence is a special case. I mean, equivalence can always be converted into an adjunction. So therefore, eta and epsilon, they have some special place in category theory. In fact, they will be natural transformations, but we haven't shown that yet. Okay. So we will do that after we look at a few more examples. Today the main purpose is to exemplify the statement that adjunctions are ubiquitous in mathematics. Okay. How many have we done so far? 8. Okay. Now, whenever you are looking at a new example, you should always think about what these morphisms are. Yeah, these eta and epsilon morphisms. Always think about them. Now I can talk about one particular class of adjunctions. An adjoint pair F left adjoint to G is called a reflection. Okay. If F is fully faithful. So, you remember the characterization of equivalence of categories? One functor is part of an equivalence of categories if and only if it is fully faithful and essentially surjective. We are dropping essential surjectivity. We are just saying, oh sorry, I'm doing it wrong. If G is fully faithful, yeah, the right adjoint is fully faithful. So we are dropping essential surjectivity and just asking for this, and reflections are quite common, and we say that if C prime is a subcategory, is a full subcategory of C, and the inclusion and I from C prime to C has a left adjoint, then we say that C prime is a reflective subcategory of C. If you remember, I have already used this word in this course. The Posetel reflection of a preorder reflection of a small category. I have already used these words. And now I'm going to justify that. Yeah, so from posets, so posets is the category of posets as objects and monotone maps as morphisms, and pre-ordered sets. Yeah, we usually use pre-or to denote pre-orders and functors between them, but here I am saying pre-ordered sets and monotone maps between them. So posets to pre-orders, obviously there is inclusion functor, but if you go in the reverse direction, pre-ordered sets to posets, how do you go like that?
We take the equivalence class of like
Identify
intersection greater.
less than or intersection greater than, or identify domain and codomain. Yeah, whenever they are both less equal, right? So this is the posetal reflection. I'm not going to write a name for this, but you understand what I'm saying. Similarly, each pre-ordered set is a small category. This is further inclusion functor, and given any category, you can construct a corresponding pre-ordered set. It's a small category. Yeah, I said just small category, and then you'll get a pre-ordered set. You obviously have a class version of this adjunction.
I mean, how is this pre-order sets? I mean, every set can be.
No. A pre-ordered set is a pair. It's a relation given on a binary relation given on a set.
Oh, so we have fixed a set.
Yeah, we are fixing a set, and we are not fixing a set. An object of this category is a set, comma, a binary relation, which is a transitive and reflexive relation.
Yeah, but for every set you will get an object in the pre-order sets.
Yes, but that's not relevant because we are never talking about the category of sets here.
This is not a small category, that's what I'm saying.
Cat is the category of small categories. So therefore, where will you send it? I'm asking for this particular question mark. Given a small category, how will you construct a pre-ordered set?
Put a morphism from A to B if home AB is.
Home AB is non-empty. Yes, if home AB is non-empty, then just have one morphism, otherwise don't have any morphism. So whether home AB is non-empty or not, that's the condition for declaring less equal. Yeah, because of composition and identity, this relation is transitive and reflexive correspondingly, and then this whole diagram is proper. Yeah, it is functorial. Whatever we said is functorial construction. Okay, similarly, maybe we should look at a more common example. Category of abelian groups into category of groups. Yeah, we said that this inclusion functor has to do with a property. We are asking for one more property, and can we enforce that property to go in the reverse direction? Quotient out by the commutator subgroup. So that's called the abelianization. I'm just going to write it as blank to the power ab, and that's a left adjoint. Okay, so this is also working fine. And I mean, what is it saying? Yeah, we are saying that given any group G and an abelian group A, a morphism from G to A factors through its abelianization in a unique way. Yes, that's what we are saying here. Maybe I should write this down. Yeah, that a group homomorphism from G to IA is in bijection with a group homomorphism from its abelianization to A. I mean, normally we would write something like this. From G to G up, there is obviously a. So for all there exists, and there exists a unique. This is our bijection, yeah. From from G to A, whenever we have F, then there exists a unique F tilde from G ab to A. And this F to F tilde mapping is our natural bijection. From F tilde you can always come back to F by simply taking composition with the quotient map. So this is an example of a reflection. In fact, AB is a reflective subcategory of the category of groups. Okay, then let's look at some examples from topology. Do you remember this K house? Category of compact Hausdorff spaces. Okay. A category of compact Hausdorff spaces embedded inside the category of all topological spaces. That's an inclusion functor. This inclusion functor has a left adjoint, which is denoted beta. Okay. But the name is stone-check compactification. If you have studied topology, then you would know stone-check compactification. Yeah, not one-point compactification, stone-check. Another example from topology is Kolmogorov spaces or T0 spaces. T0 you understand? A space is T0 if any 2 points are topologically distinguishable, which means there is an open set containing one of them but not the other. Yeah, that's T0. So topological spaces which satisfy Kolmogorov property, so they embed inside this, and obviously you have a corresponding left adjoint where you quotient out by you identify topologically indistinguishable points. Yeah, that's the equivalence relation. So that's the functor. Yeah, I don't have any name, but you can force it to be T0. Yeah, maybe I will call it T0 quotient. But observe here, yeah, in all these examples, what we are doing is we are taking a quotient. Yeah, the inclusion functor is going in one direction, and then we are quotienting out by the unwanted part to keep the interesting part. Okay, let's look at one more example, because we don't category theory and analysis, they don't really go well with each other. So what are Banach spaces?
The non-linear spaces.
Norm-linear spaces which are complete with respect to them, and norm spaces over here, yeah, with bounded linear maps, bounded linear maps. Yeah, so norm-linear spaces with bounded linear maps as the category, and take its full subcategory of Banach spaces. Then this is also an inclusion functor, and over here what can you associate to it? Completion, correct. So by this analogy, actually norm completion is also some kind of quotient. You construct something big and then quotient. Okay, so there are so many examples, yeah, coming from different areas. They are all reflective subcategories. But obviously when you define a concept and it's in category theory, you don't stop there. You obviously need to have a dual version that will be called a co-reflective subcategory. Co-reflections, I am just not going to define them, you know what it is, but I will give you some examples. So torsion abelian groups. they embed inside abelian groups. But in the reverse direction, given any abelian group, you can always take its torsion subgroup. And because we are not talking about a quotient here and we are talking about a sub-object, so we will have that inclusion functor has a right adjoint and not a left one. Yeah, so what we are saying is this. So inclusion of any torsion abelian group, I'm just going to call it B. Yeah, IB to any abelian group A is actually in bijection with, I mean, this is happening inside category of groups itself, and this is also in category of groups B to, abelian groups, not groups, because the morphisms are not any different. Under any group homomorphism, an element which is a torsion element must map to a torsion element, and that's precisely what we are saying here. Yeah, so I can add tors AB over here, and then this is the bijection. So try to understand the difference between reflection and a co-reflection. The adjoint that we are looking for, if it maps your object to some quotient, then that is a reflection. If it maps to a sub-object, then it's a co-reflection. Another simple example, yeah, I hope you know what torsion abelian group means, yeah, that every element has finite order. Okay. Then groups to monoids. Each group is a monoid.
What is this functor then? The
Torsion
torsion functor.
functor is all those elements which are torsion elements. Subgroup consisting of torsion elements.
When is an adjoint pair a co-reflection?
Co-reflection, if it is fully faithful first of all, and it has a right adjoint.
An adjoint pair, like there is a
An adjoint pair is co-reflection if the left adjoint is fully faithful.
we don't dualize fully faithful.
No. Fully faithful is property is not dualizable.
It's its own dual.
No, I mean there is no property here. Yeah, we are talking about a bijection, a set. So there's nothing dual. So groups to monoids. Every group is a monoid, and every monoid can be mapped to a group. Monoid has one invertible element, but you map it to all invertible elements. So that's the group of units. Yeah, so that's a co-reflection again. Similarly, I mean, one more example, divisible abelian groups, if you know what they are, that every element is divisible, you can divide it by any positive number. So, for example, 2 is not divisible in the group of integers, because 2 you can't divide by 2, 3. Yeah, then but rational numbers are divisible. Any number can be divided by any positive natural number. So divisible abelian groups and abelian groups, the same story. And you again have to map to all the divisible elements. Okay, so these are some examples of co-reflections. Co-reflections are not too commonly found, but reflections are more common. Somehow the co-things are not very common in nature, where nature refers to our usual mathematical world. Let me check if we have forgotten any standard examples. Well, we can like along the story of this Galva connections, yeah, we said something. Yeah, this pair is contravariant functors adjoint to the right. Yeah, you understand that? Adjoint to the right. Yeah, nothing is happening on the left. Everything is happening on the right. So that same thing we will write. So if you remember from sets to sets op, we had a power set functor. We denoted it by P star. Yeah. So P star and dual is also P star. So P star is self-adjoint on the right. Because what you have to see is any morphism from A to PB is ultimately has to do with some subset of A cross B. I'll ask you to figure out which subset, like fill in this blank, if and only if, fill in this blank, and I can swap A and B, and if and only if there is a morphism from B to PA, same way. So therefore, I mean, when I'm saying P, but I mean P star, yeah, because it's contravariant. So maybe I should say P star, P star, P star. So it's self-adjoint on the right. Yeah, please try to.
You should name those two functions differently, right? Sets to sets op and sets op to sets.
No, they are sets to sets op and sets op to sets. It's always the same thing. When you have a contravariant functor from C to D, then you can either write it as functor from C to D op or C op to D. Anyone is okay. Okay, any questions about all these examples? Are you convinced that adjunctions are ubiquitous? I'm talking about them for 1 hour. Yes?
All these restrictions, we have that the left, which category we are taking about, that is a full subcategory.
That's always a full subcategory, yes.
For all full subcategory, do we?
No. See, you are again asking the question whether an adjoint exists, whether the left adjoint exists or right adjoint exists. We are going to answer this question in one of the most important theorems in our course. It's called adjoint functor theorem. There will be 3 different versions, and if certain properties are satisfied, especially if a functor preserves all limits, then it will have a left adjoint. If a functor preserves all co-limits, then it will have a right adjoint, and there will also be the some versions of that condition. Yeah, that's our ultimate goal. Yeah, because we have already seen what limits are. And we will also prove that if a functor has a left adjoint, then it preserves all limits and dually. But now we are talking about existence, yeah, existence of this adjoint, left adjoint, right adjoint. Can it happen that a given functor has got 2 different left adjoints? The answer is yes. No, we never saw an example where it has two different left adjoints. The answer is yes, that it can have 2 different left adjoints, but they have to be isomorphic to each other, naturally isomorphic to each other. So with a unique isomorphism. And whenever there is involvement of some natural isomorphism and uniqueness up to unique isomorphism, then what is involved? Universal properties. And universal properties, they how did we define all limits? Limits are universal objects in certain categories. Which categories? The arrow category. Yeah, so we are going to use the same thing over here as well. Yeah, so this is our theorem. that given G from D to C, a functor specifying a left adjoint for G is equivalent to specifying an initial object of the arrow category A arrow G for each A in objects of C. So arrow categories will always show up. Yeah, here we are talking about the initial object version. Dually, what will be the statement? That given a functor f from C to D specifying a right adjoint is equivalent to specifying a terminal object of the other arrow category. Yeah, figure out which one. Yeah, state this theorem in the dual form. Okay, so we have to prove two different things. It's not very hard, but as soon as we talk about arrow categories, the notations become a bit complicated. Yeah, so given f as a left adjoint to G, we are going to claim that FA is definitely an object of category D. Yes, we need an object of category D together with GFA is an object of category C. That's what we want. I'm going to claim that FA comma eta A is an initial object of this arrow category. Okay, just to quickly remind you, what is the arrow category? What are the objects of the arrow category? Pairs. Okay, so tell me one object from of A to G, A arrow G. B comma A comma F. No. See, you need an object. It's always A arrow something. Yeah. So arrow is going. Where is A? A is living inside C. So therefore, this arrow should always be inside C. But it's going to another object in.
For arrow category, we have to take a object from the right.
From, yes, correct. From the other thing. So it should always be GB. Right? So this is just a reminder. So this object is called B comma F. Yeah? Object is B comma F, but F is a morphism from A to GB. That's the underlying meaning. Okay. So, I mean, this is just an aside. Yeah, don't worry about this. Let's come back to the main proof. So, do you, when I say FA comma eta A is an initial object, I first need to make sure it's an object. It is indeed an object, yeah, because eta A is a morphism from A to GFA. Yeah, let me scroll things up for you. Yeah, A to GFA. So that is indeed correct. So this is an object. Now note that, okay, now this is hypothetical. This diagram now this is a morphism in which category? I mean, it always has to be like this, GG. Yeah. So this diagram commutes if and only if the corresponding diagram in the other category also commutes. FA to FA to B. What is FA to FA? What is the corresponding thing to corresponding morphism to eta A? It is identity. If okay, see, corresponding to the identity on FA, we have a morphism eta A from A to GFA. Okay, so what we are saying that this is the corresponding morphism G, yeah, whose image we have taken here. This is 1FA, and the corresponding pair F is mapped to F bar. Yeah, F is a morphism from A to GB, and its adjoint map is FA to B. We are calling it F bar. But whatever happens, like this diagram commutes if and only if this diagram commutes. Do you see that? By naturality, exactly. By naturality of adjunction. I mean, naturality of the bijection in the definition of adjunction. If you understood naturality, then you will understand this. If you haven't yet looked at it, please go and check. Okay, so note that this happens if and only if this happens by naturality of adjunction. But what is the meaning of, like this F and G, they are arbitrary. What is the meaning of second diagram commuting? F bar equals G. Okay, so therefore there is a unique G equal to F bar such that this happens. And therefore FA comma eta A is initial. If you remember, the first triangle is actually a triangle, is a morphism in the arrow category from FA comma eta A to B comma F. So there exists a unique morphism because on the other side there does exist a unique morphism. Understood this? So this is one side. Okay. Rohan? Thinking. Conversely, suppose we are given an initial object FA comma eta A of this arrow category for each object A of C. Okay, suppose this data is given. Now given F from A to A prime, there is, now let me first draw the diagram, then you will understand what I am saying. So F is a morphism from A to A prime, so I can draw it from A to A prime. This is F. Then eta A is a morphism from A to GFA, and eta A prime is a morphism from A to GFA prime. But ultimately in this picture what you see is that there is a pair of morphisms leaving from A. The other one is a composition, eta A prime composed with F. But what do we know? We are given that FA comma eta A is an initial object. These are both objects in the arrow category. So therefore, by initial property of Fa comma eta A, there is a unique morphism over here. Now, so I can write down there is a unique morphism, but what is a morphism in the arrow category? It has to be a morphism from Fa to Fa prime. Okay, there is a unique G from Fa to Fa prime such that this diagram commutes where I put GG over here. Because every morphism in the arrow category is a morphism in the domain category. Okay, such that this diagram commutes. And hence, define FF equal to G. Okay, so this is our old trick now, yeah. We already said the initial object of the arrow category is of the form Fa comma eta A. So we described Fa for objects, and now we have described FF for, I mean, the image of morphisms under F. Okay, so functoriality of F follows from uniqueness. Always identity maps to identity, compositions go to compositions from uniqueness of G, and eta is indeed a natural transformation from 1C to GF. Because all these diagrams do commute. So eta is a natural transformation, contributing to the naturality of the bijection. I mean, there are many things to check here, but you have already seen enough proofs of this kind. So I think you are convinced.
Did you mention that the bijection is natural if there are these natural transformations?
Bijection is natural if there are natural no. If they behave nicely with respect to the categorical structure.
Yeah, but how this contributes to the naturality of bijection? Maybe we have
You just have to check. I have shown you how naturality is defined in two different ways. Let me scroll up if you are unsure. Let me scroll up over here. Naturality in B I showed you via this method. Similarly, there is naturality in A. So you just have to use naturality over here.
Can we say that F and G are adjoint if there are natural transformation eta and epsilon with eta from 1C to G?
Yes, but that's a different theorem. This is still preliminary. Yes, but they will have to satisfy certain identities known as triangular identities. We'll do that next time. Yes, so now what happens that given F from A to GB in C, there exists a unique G from FA to B such that this particular triangle commutes. Because we are working in the arrow category, everything becomes easy. Right? And this is a bijection. And this association F to G is a bijection from F is a morphism from A to GB, so C A GB to D FAB. Okay, naturality in B is immediate from the definition. Yeah, that's how we have done it. And naturality in A follows from naturality of eta. So the earlier naturality, eta contributing to the naturality of the bijection, like this uniqueness will contribute to the naturality of the bijection required in eta, the components of eta, and here naturality of this bijection F mapping to G in A component, it follows from naturality of eta. And this is the end of the proof. It's an abstract theorem, but it can be used very easily to prove uniqueness of adjoints. Like left adjoint is unique up to a unique isomorphism. Because everything is about initial objects and initial objects are unique up to unique isomorphism. So let's stop here for today.